the Carlist rank of polynomials with low weight.
I would like to thank the organizer for this opportunity to talk in this great conference. I'm going to talk about Carlist RAM with for polynomials of low weight. This work is in collaboration with Michele, my PhD student. Well, some notation, Fq is a finite field with Q elements. We consider a polynomial, and we say that a polynomial is a permutation polynomial of over Fq. The math that F defined over Fq is a permutation. Two polynomials represent the same permutation. The function that the function defined are equal for all A in the field. That is equivalent to F congruent to G mod F power Q less X. In general, we can construct a set of permutation polynomial, and in fact, that is a group. And one result about from Carlist in 1953 that say that this group can be generated by the linear polynomial and the polynomial F power Q minus 2. That means that if we take F a polynomial, we can find a polynomial of this form. This form that is a composition of linear polynomial and that this function. We had some restriction that A0 is 2, 8n had to be different of 0. And the polynomial, this polynomial had to be congruent with F. Then we had the following definition. We had a polynomial, that's a permutation polynomial. The small n which there is a polynomial Pn, or that form, this form, such that F is congruent with P. We call that is the Carlist RAM is exactly the number of inversion function. We say the inversion function because when we calculate S power Q less 2, that is equal to S power minus 1 when X is different than 0, and 0 is X is equal to 0. It's essentially an inversion. Then we can represent the polynomial P of this form like a fraction, a continuous fraction. And following the theory of continuous fraction, we can calculate the convergence of that fraction. The last convergence is this. Is this. And in a state, we obtain this denominator that is clear that cannot be 0. This constant can be calculated by recursive by this relation here. This is a classical result about continuous fraction. Then we had a zero dot point with when we can calculate this fraction, and then you had that f will be equal to this fraction for all f x in q. Fq less the set of poles. They follow from this relation here that we can find a relation between the calogram and the degree of the polynomial f, because if we take this relation, multiply it by the denominator, then we obtain a polynomial, and this polynomial has this number of zeros. Then the number of zeros had to be greater than the degree of the polynomial. Then we had this result from this author that the permutation polynomial of degree d and Cayley rank n, then n had to be greater than q minus 1 minus d. That is a consequence of the representation. Now, other question is how to find a relation between the Cayley rank and the weight of the polynomial. The weight of the polynomial is the number of non-zero coefficients of the polynomial f. This result was found by Gomez Perez, Stafford, and Toposoglu, that say that if we had a permutation polynomial of degree at least 2 and had this representation, this is a weight, and if the polynomial is different that this binomial, essentially binomial, then the Cayley rank is greater than this number, q over the weight plus 2 less 1. Or equivalent, we can find a lower bound for the weight from the Cayley rank here. Then we had two questions. If we had the Cayley rank small, can we say about the weight? Or if we had the weight very slow, can we say about the Cayley rank? Then, in fact, this relation is not optimal. For example, for Cayley rank 2, we had the following proof of the form. This word is with Oliveira and me, or Jose. If we had a finite field with characteristics O and a permutation polynomial with Cayley rank 2, then we had this limitation of the weight. It's essentially q less q over the characteristic. This value is very slow. The idea of the proof is very simple. If we had the Cayley rank is 2, then we can write f, or f is equivalent to this series, this polynomial, with A, B, C, D in FQ. Some of them are different of 0. Then if we want to estimate the number of or coefficient different than 0, we need to determine how many solution has this equation when the index is here. Essentially, we had this lemma. If we this equation is equivalent to something like this, then that is essentially a function that is periodic, that the period is the divisor of the q less 1, and this function is periodic with period p. Then we had this inequality. Some technical details, we obtain the result, this result. Then we fix the Carly run small, and we obtain some condition on the weight. On the other hand, if we take the small weight, we have the following result. In process. Then we had a permutation polynomial of degree greater 2 and weight n less than the root square of q, a Carly run equal to k, and we are going to suppose that the k converse of the polynomial Pn is of this form with a, b, c, d different of 0. It's possible that a can be 0. I don't remember well. Then we can obtain a lower bound for the Carlys. Essentially is q less 1 less a constant. And here we had this exponent that is less than 1. This bound is very good when n is small, but when n is close to a square root, it is not very good. The idea of the proof depends on some lemmas, technical lemmas. The first lemma is that if we take a set with k elements, except that p represents the poles of the representation of the function f with Carlys rank k. Then we can choose some gammas that had this property, that the union of these sets is less than a function f and k that satisfies this recursivity. This f1 is the identity, and this depends on the f2 rate. This is the one lemma, and we had that that function fn is less than q less 1 for all h less than a constant cn that we can calculate exactly in the case C2. And for n greater or equal to 3, we had this inequality that essentially we had that function is decreasing, that had only one point where that inequality happened, and we estimate the value of C. Then finally, using that lemma, we had this lemma that say that if we had a Cayley-Grant with that hypothesis of the theorem, then the Cayley-Grant is great that the constant C n when n is a weight of the polynomial. The idea is some classical. We take a polynomial f that had weight n and Cayley's rank k. Then we can choose gamma 1, gamma n plus 1, such that this system of equations k plus 1 equation is true for almost q less fn k different value of u. Yeah? Essentially, if we think that one equation is true for q less k, where k is the number of poles, and again, then we can use the other equation, and we had that had to the point when don't satisfy this relation has to be very small. Then we consider this vector, and we had n plus 1 vector that in a space of dimension n, then there are linearly dependent, then we can find C1, Cn plus 1 not all equal to 0, so that we had the relation that the sum of these vectors is equal to 0. Using this equality here, we obtain this relation. And the relation is equivalent to have this polynomial here, and we take the denominator, multiply the denominator, we obtain this polynomial, and we prove that this polynomial is not identically equal to 0, and thus had almost q less n k value of u where gu is equal to 0. Therefore, we had that the degree of g had to be greater than q less f n k. And the degree of g is n plus 1. Then we had this inequality. But the previous lemma, we proved that the equality less or equal is true for all c less than cn. Then that implies that k had to be greater than cn. That complete the proof. And essentially, we had the comparison of the result. This is the original result of Perez, Ostafi, Topos loop. This is a result with Jose for Cayley-Grant 2, and this is a result with Michele with weight less than square root of q. We had this inequality. That is all. Thank you very much. I don't know. It's very difficult. Very difficult to calculate.
Why?
It's difficult because I need to find how to write the s power n integral and the inversion and linear function. I don't know how
open?
begin. I don't
It's
know.
open?
Huh?
Is that open problem?
This. This.
Other questions? So let's thank our speaker again.
Thank you very much.
Valeu, Fábio.
Obrigado. Olha só, gente. Pessoa, hein? Deu 20 minutos falando. Tá?
You can put over the ear. Yes. It's off now. When you start talking, you just move this. You can put this. We are transmitting the conference on YouTube. Do you mind if we transmit your talk, or do you not want it to be transmitted? We can do it. So, transmission, yes.
Yes.
Okay. So here's the pointer. Forward. Right. And this red one is the laser. This one. Yes.
This one?
Yes. That's precise.
Thank you. Hi.
Hi.
Nice to meet you.
Nice to meet you.
Luis. I'll introduce you, Satoru Fukasawa. Is
Ah,
that
yes,
correct?
yes, correct. Thank you. Oh.
Hello, everyone. So we're now ready for the second talk in this afternoon. It's our pleasure to have Satoru Fukasawa speaking about Galois points and rational sets with Galois points and rational functions with small value sets.
Thanks for introduction. I talk about Galois points and rational functions with small value sets. My result in this talk have been published in Hiroshima Mathematical Journal. The bottom of this slide is advertisement. Yoshihara and I wrote list of problems. Please visit my site if you are interested in. Okay. I explained the theory of Galois points. Let's keep an algebraic closed field of characteristic P, which is 0 or positive. Let's see an irreducible plane algebraic curve of degree D, at least 3. We take a point P in the projective plane. Then we have a natural rational map from C to the projective line, which is called a projection from P. This is a curve C. We take a point P. Then, and we take a point Q. Then we have the image by PQ, like this. Yoshihara introduced the notion of Galois point in 1996. A point P is called a Galois point if the field extension induced by Kc over Kp1 is a Galois extension. We have a natural problem. How many Galois points? Points on C, if a point is Galois and the smooth point of C, then we call such points inner Galois points. The number of inner Galois points is denoted by delta C. When we consider delta C, we assume that D is more than or equal to 4, because the natural problem is trivial if the degree is 3. When the Galois points are not contained in C, we call such Galois points outer Galois points. The number of outer Galois points is denoted by delta prime C. When C is smooth, the answer to the natural problem is as follows. Gathering the result of Miura Yoshihara, Honma, and me. The last paper of mine was published in 2013. Assume that C is smooth if delta C is equal to more than or equal to 2, or delta prime C is equal to or more than 2, then C is one projective equivalent to one of the following curves. For inner Galois points, there are 3 types appeared. The top is the Hermitian curve, which is the Feldman curve of degree Q plus 1. The second is a special curve in characteristic 2. The third is the chaotic curve defined by x3 plus y4 plus 1 equals 0. For outer Galois points, there are 4 types. The top is the Hermitian, and the second is Klein chaotic in characteristic 2. The third is the Feldman. The fourth is a special curve in characteristic 2. Furthermore, for the case of characteristic 0 and outer Galois points, the answer is as follows. Gathering the result of Yoshihara, Duyagait Miura, me Takahashi, the last paper is written in this year. Let C be irreducible, maybe singular curve. When P is 0, delta prime C is 0, 1, 2, or 3. The last case occurs if and only if C is projectively equivalent to one of the following two plane curves. One is the Feldman curve, and another is the image of the map from P1 to P2, given by SD, S plus TD, and TD. The main theorem in this talk plays an important role for proving this theorem. I explain rational functions with small Bari sets over finite field. Let f be a non-constant polynomial over Fq. Vf is a Bari set represented by f alpha. It is not difficult to prove the following lemma. The size of the Bari set is lower bounded and upper bounded these numbers. The upper bounded is trivial, which is the number of elements of Fq. The lower bound is Q over degree F rounded up. To prove the lower bound, we consider the fiber of F. The fiber contains at most degree F elements. Therefore, we have this lower bound. There are two papers by Carlitos Mills, Strass, and Mills written in 1960s. They studied functions attaining the lower bound. They determine f with attaining the lower bound in some cases. F is called a polynomial with minimal value sets if the lower bound attained. We call MVSP in this talk. I introduce an interesting theorem according to Borges. To explain easier, I explain a weak version. Assume fx and gx are defined over Fq. And the difference of these functions in two variables is irreducible over Fq bar. Then we have the following. If the curve defined by fx minus gy is Q-frequency non-classical, then fx and gx are MVSP with the same value set. When the value set contains at least three elements, then the converse also holds. Borges' theorem presents relation between Q-frequency non-classicality and MVSP. C is called Q-frequency non-classical if for any smooth point, the image under the Frobenius map is contained in the tangent line. This notion appeared in the study of steel bulb. FR is the Frobenius map, and TQC is the tangent line at Q. I explain another version of a theorem of Borges, which is used later. Fx and Gx are MVSP with the same body set. And the body set has at least 3 elements. Then, for any irreducible component of the curve defined by the difference over Fq is Q Frobenius non-classical. We consider rational functions over finite field. H is represented by Fx over Gx, where F and G are relatively prime. Degree of H is defined as the maximum of degree F and degree G. We have a map from P1 to itself, homogenizing F and G. The body set of H is denoted by VH tilde in this talk. Similarly to the case of polynomials, we have the following lemma. Lower bounded and upper bounded these numbers. Then Bartoli, Borges, and Kuos prove the following theorem. The field extension coming from H is a Galois extension. Then the number of values is equal to the lower bound or the next. They prove that the value set is very small. What relation does there exist between Bartol-Borges, Kuos theorem and Galois theory? The main theorem gives an answer. I explain my result. Let C be defined over Fq and irreducible over Fq bar. P1 is a point 100 and P2 is a point 010 in the projective plane. First, I explain the first half of the main theorem. Assume that P1 and P2 are Galois points such that any automorphism coming from GP1 and GP2 is defined by Fq, where GP1 is the Galois group comes from the Galois extension according to Galois points. Further, we assume that the group generated by GP1 and GP2 is a finite group. Then we have the following. There exist 4 polynomials F1, G1, F2, G2 over Fq such that the following four conditions are satisfied. A and B is a natural condition. C and D is crucial. The defining polynomial of C is an irreducible factor of f1x g2y minus g1x f2y over fq. This polynomial comes from the equation of rational functions. In condition D is a fixed field by the generated group generated by these rational functions. These rational functions. I explain the second half. For polynomial be as above. If the order of generated group is the order of GP1 times the order of GP2, if and only if C is defined by f1x g2y minus g1x f2y equals 0. If the generated group is the semi-direct product of GP1 and GP2, if and only if Fqy over Fqh2y is a Galois extension, where H2y is defined as F2y over G2y. Assume two Galois points are external, then we can take G1x and G2x is equal to 1. Therefore, defining polynomials of C is an irreducible factor of f1x minus f2y over fq. Main theorem and Bartoli-Borges-Kugos theorem imply the following corollary. F2x and G2x are as in main theorem. If the generated group is the semi-direct product, then the size of the value set of H2 is the lower bound or the next. Main theorem and Borges theorem imply the following corollary. P2 and P2 P1 and P2 are external Galois points. F1x and F2x as the main theorem. If F1 and F2 are MVSP with the same value set, and the value set contains two or more elements, then C is Q-Fubens non-classical. These corollaries present a relation between Galois point and rational function with small value set. I explain outline of the proof of main theorem. P1 is a point 1, 0, 0. Since P1 is 1, 0, 0, we have that pi P1 is represented by Y1. Since P2 is 0, 1, 0, pi P is represented by X1. The fixed field by the generated group is rational according to Luro theorem. This field is a subfield of the projection, subfield of the field coming from pi p1. Therefore, we can use Euro theorem. A generator is denoted by T. Then we have this relation. T equal G2, F2y over G2y equal F1x over G1x. This relation gives relation appeared before. We have the following diagram. This is the function field of C. This field coming from Galois point P1. This is coming from GP2, and this coming from generated group. The T is represented by two functions. These guys. That's all. Thank you.
Any questions for the speaker? Not, let's thank him again. And we have a couple of minutes until the next talk.
Thank you very much.
Thank you.
Nesse momento tem 3 minutos. Eu também descobri agora. Se você falou assim, o Luiz pode também é. Sim. Tem um bairro inteiro.
E a praça Luiz Final.
Verdade. Você falou. Legal, sério. Eu sei se ele estava sentando ali agora, na minha frente. Deixa eu roubar um pouquinho da água de mim mesmo, depois eu volto para. Tá.
Oi. Acho que sim.
Hello, everyone. So we're ready for our third talk this afternoon. Before the talk, I just wanted to remind everybody that the talks are being streamed at YouTube. Just look for ICMC, and you can find the links for the talks. So our next speaker is Alex Campos, who is going to talk about extendable Galois points for singular plane curves.
Thank you, Luis. I'd like to thank everyone who made this possible, especially Erivelto, and all the people helping here. So I will pass over again some of the definitions Professor Satoru just passed. But let me start by fixing some standard notation. So for us, K will denote an algebraically closed field of characteristic P, which can be 0 or greater than 0. P2 is the projective plane over K. The line passing through two different points in the projective plane will be denoted by the 2 points and a bar over them. Cn is the cyclic group over the N. This here will be the direct product of ecopies of the group Cp. P here is the same as the characteristic of the field. And this difference C here will be an irreducible plane curve of degree D. And I will use sing C to denote its set of singular points, Kc its function field, and for a point of the projective plane, I will denote by MP the multiplicity of the point of the curve at the point P. The definition is the same Fukasawa just gave, just the picture here is different. We take a point in the projective plane and a line not contained, a point not contained in this line, and this map here, which assigns to each point of the curve the point that you get when you intersect the line joining P and Q with the line L you fixed beforehand, is the projection from this point P right here. And this projection induces a field extension from the function field of the line to the function field of the curve. And when this extension, here are some other properties of this extension. For instance, it has degree D minus MP, where MP is the multiplicity of the point from where you are projecting. When the point is given by this 1, 0, 0, you can represent the extension as k of x and y over ky, where x and y satisfy this equation, f of xy equals 0, where f is the affine equation for the curve C. This extension will be inseparable if and only if the curve is strange and P is its nucleus. And we say that the point is a Galois point for the curve if the extension, the corresponding extension, is a Galois extension. And we will denote the set of outer points. By outer points, I mean the points not lying on the curve. By inner points, I mean the points lying in the curve. Well, the outer points will be denoted by delta prime, the its cardinality by, the set will be denoted by capital delta, its cardinality by delta prime, and the inner points won't have any delta, won't have any prime. All right. So here are some problems that naturally arise from the definition. And these two here will be what I will be most concerned. Given a curve C, how to determine all the points which are Galois points for this curve. And given a Galois point for a curve, what is the structure of the group, of the corresponding Galois group? Well, for non-singular curves, these problems have been thoroughly studied by Fukasawa, Homa, Yoshihara, and many others in Japan. And inspired by what happened in the non-singular case, there's this definition right here of extendable Galois points. So before giving the definition, let me note that if you take a Galois point, any automorphism from the Galois group induces an automorphism of the curve. And I will say that the point is extendable when for every sigma in the Galois group, the corresponding automorphism of the curve can be extended to a projective transformation. And the extendable sets, the sets of extendable outer and inner will be denoted just before, but with an index E. So if a curve is non-singular of degree at least 4, any Galois point is extendable. This follows from classical result of Segre, which was later strengthened by Shang. Well, the first and most important results to study Galois points, extendable Galois points for singular curves, are these two, and they basically say that we know exactly what the equation for the curve is when it has an extendable Galois point, and it depends only on this difference right here, the degree of the curve minus the multiplicity of the point. More exactly, it depends on whether this difference here is 0 or not modulo p. If it's not 0, then the equation, the curve is projectively equivalent to a curve of this equation, and the corresponding extendable Galois point is this one. These polynomials f here are homogeneous of degree the index, and the Galois group is cyclic, and we can represent it by this matrix right here. The idea here is nothing very sophisticated. There's a morphism from the Galois group GP to this group, the multiplicative group of the field K. And the order of the Galois group is exactly D minus MP, which is not 0 modulo P, which forces this map here to be injective. Therefore, this group here is cyclic, and after a suitable projective transformation, the field extension is this one, which has this equation. And when d minus mp is 0 modulo p, the equation has this form. Here, this little f is an additive separable polynomial with respect to this first variable here. And these two polynomials are homogeneous of degree mp and d. In particular, this result here implies that this L, when you write the difference d minus mp like a power of p times a number not divisible by p, this number here, L, cannot be anything. It must divide p minus p to the e minus 1. And in this case, this map is no longer injective, so it will be a semi-direct product of an elementary abelian P group and a cyclic group. And this extension here is elementary abelian, from whence it comes the little f, and the other part of the extension is cyclic, and from here it comes the f to the L. Now some facts about Galois points. A generic curve does not have non-trivial automorphism. So a generic curve won't have any Galois points also. If P is an inner extendable Galois point, which is non-singular, then it must be a total flex, total inflection point of the curve for the curve C. Curves with infinitely many outer Galois points exist, and they are strange and rational. Curves with infinitely many inner Galois points also exist. Let me just briefly recall what a strange curve is. We say that a curve is strange when there's a point which when you take all the tangent lines to the curve at all the points of the curve, they all pass through a common point. When this happens, we say that the curve C is strange. We know everything about Galois points for non-singular plane curves. This was finished by Professor Fukasawa in 2013. Now, the first of the results I want to tell you is this one. A curve of degree not 0 modulo P can have, of degree at least 3, can have at most one outer extendable Galois point. And when it has one extendable outer Galois point, it is projectively equivalent to this curve here. And the corresponding Galois point is this one. Right. The proof is very geometric in nature. Let me try to convince you. So if we take a curve that has one outer Galois point, it must have this equation by this previous result here. This one. Just have to plug MP equals 0. But then all the singular points for this curve are contained in this line, x equals 0. And moreover, every point that lies in this intersection here, be it singular or not, has only one tangent line, and this can be seen by factorizing this polynomial here. And this only tangent line intersects the curve C at only the point, the corresponding point. So the situation can be represented by this image here. The blue point here is the Galois point, and these red dots here are the points of the curve lying on the line x equals 0. So if the curve had two singular points, two distinct singular points, then the set of outer Galois points, extendable outer Galois points, must be contained in their intersection. But this intersection here is a singleton, because any two distinct lines in the projective plane intersect in just one point. So if the curve had two different singular points, you would have just one outer extendable Galois point. So we can suppose that the curve has only one singular point with multiplicity ms. And now for each extendable outer point, if it had more than one, for each one, there would correspond d minus ms total flexes of the curve, because each point, each of these red dots, there are non-singular points of the curve, are total flexes. And then the line x equals 0 intersects the curve in d minus ms non-singular points. So we have d minus ms total flexes. And this occurs for every extendable outer Galois point. And if you had at least two Galois points, you can act with the group of one Galois point in the other point, and this would give you at least d plus one other Galois points. And then you would have a total of d plus 1 times d minus ms total flexes. But the curve C has only d minus ms total flexes. Therefore, it cannot have at least two. This situation is depicted right here. So this red dot is the singular point. It has only one tangent line. All the Galois extendable outer Galois points lie on this tangent line to S. And for every of these Galois points, you would have a line that pass through S and contain d minus ms total flexes. So the other two results mentioned are about extendable outer points when D is 0 mod P. And in this case, if the curve has at least two, then it has infinitely many. And the equation is this one. Here I take P to be at least 3. But the case P equals 2 was taken care of by Fukasawa. And the last result is this one. If D is not 1 modulo P, and the degree of the curve is at least 4, then we have that the curve has at least two inner extendable Galois points, if and only if it's given by this equation. And this curve right here has infinitely many Galois points. So here's the proof, and that's it. Thank you.
Any questions for Alex? Okay, so if not, we have a coffee break. We have 40 minutes, I think, until the next two talks to end the day. All right, see you then. Let's thank the speaker again, please. Okay, so it's time to start our last session of today. It's my understanding there's a reception after in the afternoon at 6. If you want more details, ask Erivelto or somebody in Orange. But for now, we have our last talk. Nazar Arakelian is going to talk about a characterization of double Frobenius non-classical space curves.
Thank you. First of all, I would like to thank the organizers for the opportunity to give this talk, to share my work with you. And thank you all for being here, attending this talk. And this talk is based on a joint work with Erivelto Borges. And I will present a characterization of double Frobenius non-classical space curves. Oh, of course, Fq is a finite field over order Q. And we know by many reasons, many applications, that one of the most interesting problems involving curves over finite fields is the construction and the understanding of curves with many rational points defined over Fq, many Fq rational points. And by many rational points, we can have different directions. Of course, the main one are the maximal curves presented by Maria this morning, and Hagashini also talked about something about maximal curves, and you all know the definition of maximal curves. But in this talk, by many points, I mean the following. Okay, denote by NQ. Oh, I don't have to look. The number of FQ rational points on a curve in Pn, on a curve X in Pn. Okay, assume that the degree of this curve is D and the genus is G. Okay, if this curve is what we call Fq Frobenius classical, and I will give the precise definition of Frobenius non-classical curve in a couple of minutes, but Professor Fukasawa gave us a taste of what it is, which for plane curves is precisely this property that at the general point, the Frobenius map sends the image by the Frobenius map of a general point lies on a tangent line of the same point, okay? But this for space curves, we have a different definition, but the point here is that if the curve is Frobenius classical, then the number of points is bounded by this number that depends on the dimension and the genus and the degree of the curve X. Okay, again, the curve must be Frobenius classical to this bound work. However, I will not give the mathematical proof of that, but we know that a general curve is Fq Frobenius classical. So let's say that this bound works for almost all curves. Okay? Hence, to obtain a curve that has more than this number of points, you must look for what we call Fq Frobenius non-classical curves to find a curve that exceeds this number of points. Okay? So this is the concept of Frobenius non-classicality. Again, I will give the definition in a couple of minutes. A concept that at principle parallels this one of Frobenius classicality is the concept of duality of curves. So take an algebraically closed field K and consider the dual projective space of dimension n, which is the points in this space are precisely corresponds to hyperplanes of the projective space. Okay, and so if you have a curve X, you consider what we call the strict dual curve of X, which I will denote by X prime, which is defined as the closure in the dual projective space of the set of osculating hyperplanes at the non-singular locus of the curve. Okay, and this is the strict dual of X. And the map that sends P to the osculating hyperplane, the point that corresponds to osculating hyperplane in the dual projective space is called the strict Gauss map of X. And we can extend this to a cover, which by abuse we call it strict Gauss map of X. It's a rational map that sends your curve to the dual curve. When the characteristic of the ground field is 0, then we have this nice property that the dual of the dual is again X. This is what I will call the bidual property. And if you call gamma prime the Gauss map of the dual curve, then the composition of the Gauss map of your curve with the Gauss map of the dual curve is the identity map. Lucky for us that, in particular, in this case, the dual is non-degenerate. This means that it does not lie on a hyperplane. But this situation does not necessarily hold in positive characteristic. So if characteristic is positive, then both separable and inseparable degrees of the Gauss map can be positive. Okay, but how do we care? Because our motivation is this very nice result by Professor Garcia and Professor Volok that shows the following. You take a smooth non-classical plane curve, or if you take a smooth non-classical plane curve. Then you have this bidual property if and only if your curve is defined over Fq and it is Fq, Frobenius non-classical. And in this case, the composition of the Gauss map of gamma and gamma prime is not the identity map, but it's actually the Frobenius map. Okay? And this is our motivation. But as the title of the talk said, we're going to study double Frobenius non-classical curves, space curves. Okay? And if we look to plane curves, then we have only one double Frobenius non-classical plane curve, which is this curve. It's a nice result by Erivelto Borges. If you consider two integers, u and m bigger than 2, co-prime integers, then the curve defined by this polynomial is the only Fq to the u and Fq to the m Frobenius non-classical plane curve. And pretty much everything is known about this curve. In this talk, I will call this the Borges curve, if it's okay. But when we increase the dimension, we don't have a unique curve, double Frobenius non-classical curve, even for space curves. So, okay, this result by Garcia and Volok gives a characterization of Frobenius non-classical curves, in a way. Okay? So, my intention here, our intention is to do the same for double Frobenius non-classical space curves. Not the same, but I would say, do what we can do, what I can do. Okay. So, after the half of the talk, I will give the preliminaries. So we consider always a curve, a space curve in P3, with this order sequence, y0 to y3. So this sequence is the sequence of integers that are realized as intersection multiplicities of planes with your curve x at the general point. And we say that the curve is classical if the sequence is the classical sequence 0, 1, 2, 3. Otherwise, we say that the curve is non-classical. Okay. Now I thank to Hagashini talk. He already introduced the concept of osculating plane. So given a non-singular point, the osculating plane to x at this point is the unique plane such that the intersection multiplicity with this plane and the curve is the highest possible. Okay. Okay. Now our curve is defined over Fq, and this is the definition of a Frobenius non-classicality or Frobenius classicality. So assume that your curve is defined by these affine coordinate functions, where x is a separating element. Then there exists a sequence of 3 integers, 0, me1, me2, such that this function is non-zero in the function field. And this sequence is known as the Fq Frobenius order sequence of the curve. Fq Frobenius order sequence. If you change the ground field, if you take an extension, the sequence can change as well. Okay? And again, the curve is said to be Fq Frobenius classical when the sequence is 0, 1, 2. Otherwise, we say that the curve is Frobenius non-classical. As I said before, for plane curves, this being Frobenius non-classical is equivalent to this, okay? To send a general point. The Frobenius map send a general point to the tangent line at the same point, okay? In higher dimensions, we don't have this equivalence. But the property of the curve, for instance, space curve, if the Frobenius map send the point to this tangent space, osculating space to this point, then your curve will be Frobenius non-classical, but the converse in general does not hold. We know that the Frobenius order sequence is always a subsequence of the order sequence of our curve. And it can happen that, for instance, if epsilon 2 is bigger than 2, then what will happen is that you can have what I call artificial Frobenius non-classicality, because if epsilon 2 is bigger than 2, then overall extension of Fq, your curve will be Frobenius non-classical. So in this work, and in particular in this talk, every time I say that your curve is Fq Frobenius non-classical, I mean that the image by the Frobenius map of a general point is in the osculating plane to the curve at this point, okay? A last definition that I will need, already introduced by Alex, is the concept of strange curves. A curve is strange when all the tangent lines meet in a common point, or not necessarily all, but in the non-singular locus of the curve. And in this talk, we always assume that our curve is non-strange. Okay? Okay. So we begin our result. Now we present our results. We start to present our results. Okay. So we first study the double Frobenius non-classical curves, such that the strict dual is degenerate. Okay. So consider a curve in P3, U and M coprime integers, M bigger than 2. Then the following conditions are equivalent. Your curve is double Frobenius non-classical, and the strict dual is degenerate. If and only if epsilon 3 equals k to the u, and x lies on a cone over the Borges curve defined over Fq. So I think that this is very interesting, because when the dual curve degenerates, then somehow is related to the only double Frobenius non-classical plane curve. Okay? And so you have a cone, you have a projection that sends your curve to the Borges curve. In particular, we have a nice criteria to decide whether or not your curve has a degenerate dual. Okay? So if you have a double Frobenius non-classical curve, again, M bigger than 2, okay, M and U coprime, and your curve is Fq to the U and Fq to the U, Fq to the M, Frobenius non-classical, then if epsilon 3 is not Q to the U, then you know that your strict dual is non-degenerate, okay? And you can, assuming that your curve is double Frobenius non-classical with degenerate dual, you can obtain many, many properties of this curve. For instance, I will show only one. If you have a double Frobenius non-classical curve such that the dual is degenerate, then the degree of the projection, recall that in this case your curve lies on a cone over the Borges curve. And the degree of the projection coincides with the separable degree of the Gauss map of X. In particular, if the Gauss map is purely inseparable, then your curve must be birationally equivalent to the Borges curve, the model in P3. Okay. Okay, now we can move on to our main result. Okay. We're always assuming that in every previous result, we're assuming that m is bigger than 2. If m equals 2, then so consider a curve in P3, assume that it is Fq and Fq squared Frobenius non-classical, then the dual curve X prime is always non-degenerate in this case. So we are okay in this case, we don't need any criteria. Okay, and a key result to obtain our characterization is the following. Consider Fq Frobenius non-classical curve with this order sequence. This not only in P3, but in any dimension. With this Fq Frobenius order sequence and, this order sequence and this Fq Frobenius order sequence. And assume that the strict dual is non-degenerate and the last elements here of the order sequence and the Frobenius order sequence are equal to a power of p smaller than q. Okay, this property of these two numbers being equal means that that the Frobenius non-classicality is of the type sending a general point to the Frobenius map sends a general point to the osculating hyperplane at the same to the curve at the same point. Okay, but in this case, if all this happens, then the strict Gauss map is purely inseparable of degree p to the r. Okay, and with this on hand, we are able to give our characterization. So consider a curve in P3 with this order sequence. Of course, I didn't mention, but it's always there. P bigger than 3, okay. With Gauss map gamma prime and two integers u and m. Then the following conditions are equivalent. Q to the u is bigger than epsilon 3 and x is double Frobenius non-classical. If and only if epsilon 3 equals p to the r for some r. The dual is non-degenerate with this order sequence, okay? You have this nice B-dual property. The composition of the Gauss maps is the Frobenius Q to the M map. And moreover, the Frobenius Q M minus U, the Q M minus U Frobenius order sequence of X prime is this one. So we have somewhat characterization of double Frobenius non-classical space curves. And just to finish, just a remark, thanks to a result by Professor Roma, you see here the orders, in this case, when your curve is Frobenius non-classical with this condition, then you have this order sequence of the curve, and the epsilon 2 and epsilon 3 are both powers of p. And in this case, we know by result of Professor Roma that your curve is non-reflexive and the tangent space is non-reflexive as well. So let's say that if you want to construct space curves that are non-reflexive with non-reflexive tangent spaces, you can just construct a double Frobenius non-classical curve and take the strict dual. And well, that's all. Thank you. Equations. Okay. I do have, but I can't remember right now. But yes, the answer is yes, I do have. Let me think. Obrigado. Thank you.
Thanks. So you're going to be at 6 at the reception location, but you guys already received an email with the full address, so feel free to go directly there, as long as you be there, at 6, or at least not before 6. Otherwise, you can also stick around. And I mean, some of us will be just stay around for a few minutes, maybe 30 minutes, and around 15, let's say 5:45, we should be leaving and getting there at 6. So it's up to you. If you want to stay around, I mean, just join us in half an hour, let's say. Otherwise, you can just go by yourself if you have the address. Okay. The name of the place is El Cardal. I'll just write it here. So you can just Google that up if you want.